are listening to Gabriel, who will tell us more about the contaminants and parasites affecting algae cultures, identification, isolation, and possible solutions. After Gabriel, you will hear Anna, and then Jurita after the Gabriel.
Thank you, everybody. Wait a little bit until you are all seated. This would be more interesting after the part of the macroalgae, the part of the Eureka, the part of Anna. But I think all of you here know a little bit of culturing algae or the contaminants of what we have in the water when we have some algae. And all the organisms that we can see on the cultures that we normally have on open ponds or greenhouses or photobioreactors, normally it's not going to be just the algae that we have. All these organisms that live with this algae is going to be there mainly because we have air inside of cultures, or we have some leaking on our cultures, and then we have contact with other species, or even the hands of us that we are managing the algae. When we are managing the algae, we're introducing new organisms, new bacteria, new fungi to the cultures, and this may be a compounding fauna for our cultures or some contaminants. And all these organisms may be some grazers, some larvae, some rotifers, some tintinids. All of these can come with our culture and not really be a contaminant for us, because the contaminants, what's the contaminants? They are the organisms that are going to collapse our cultures. So what I want to say is they are the organisms that are going to be present on there. They are the organisms that's going to be with our cultures, the same as the other organisms that we have there, but they are going to cause some prejudice on our culture. They are going to make our cultures take less biomass on the end, because what we want is a lot of biomass from a week of culture or 15 days of culture. But we are not going to have this because of this same type of organisms, depending of the genus, depending of the species. This is what we want to identify. This is what we want to know if these organisms that we have there on that moment, they are prejudicial for us or they are not prejudicial for us. So to know that, we need to know what type of contaminants we have and what they can look like. And from now on, everything that I will say, it's really easy to find. If you Google it, if you Google your species and contaminant, probably you are going to get really close from the species that you want, from the species that you are looking for, and how to prevent it from your culture. And there are a lot. We have from amoebas like Vampirella that you know that consumes the inside of our organisms and take everything out, and we just don't see it growing. From one day to another, you have a bloom of it, and it takes out our culture. You have some tintinids, some forticellas that they may consume your culture in less than 2 days. You can have no culture anymore because of that. You can have some other algae. Sorry, this is an example of a type of grazer that would not affect my culture. In this case, why it doesn't affect my culture? Because these organisms, they are really much more small than my algae. You can see that they have some dots inside. These are the organic matter on the media that they consumed, but they couldn't consume it because they are so small compared with my algae that has 150 micrometers that it wouldn't even bother the algae. Here's a little video that I did. You can see the algae, they are the moons. This is Pyrosis lunula. They are really big. And you can see around it, you have these moving things that are the grazers that are out around, and they just help my culture to not have more contaminants in reality. So in this case, this type of grazer, it's even helping me on my culture. I wanted to show you this to show that not always this grazer, this same grazer that on a chlorella culture is going to collapse my culture, it's not going to make any difference. Sorry, chlorella not, because this is a seawater species. So it's due to the non-chloropsis salina culture, it will collapse with this algae. So with that, another algae that can contaminate your on cultures. Imagine that you have a Bacillariophyta culture that you want to do some cultures for feeding fish. And on this feeding fish, you have, on this feeding, you have your diatoms, they are growing, they have nice color. And from one day to the other, you have some green color coming from your brown culture. This is probably happened with some of you. If you culture algae, this is going to happen to you at some point, because you have some type of algae that grow much faster than other algae, and they use virtually the same conditions to grow. And if you don't take care, and don't take care is like not passing a little bit of more alcohol on your hand, you're already going to contaminate one culture to another, and you can lose all the culture that doesn't grow so fast on this type of environment. And then you are going to have something like this, and then the other day you have no more diatoms and you have just green algae growing on your culture. So other things that you can have is some yeast and some bacteria, some fungi that you can have on your algae, and you are always going to have this type of organisms on the culture. That's the thing. However, you have to take care when they are going to attach to your cells, and when you see that they are taking your culture down, or they're making the growth of your culture is lower or something like that. This is the experience that we had on our lab. I think you can see everything. Let me just take this window out. Like this, yeah. So as you can see here, I have a Phylodactylum tricornutum. On this Phylodactylum tricornutum, all these are fungi that they are growing attached to my cell wall. And this really killed my algae. All my algae, I was first thinking, it's just a fungi. It's normal to have some fungi on my algae. And 2 days after, I had no culture at all. So I had to start again. I had to identify this fungi. I had to put some fungicide inside of it before I could have it growing again. So another types of contaminants that we can have, and we don't, this is another fungi that is really common on Hematococcus pluvialis, that if you grow Hematococcus pluvialis, in a moment, you are going to have this type of problem. That is, the Paraphysoderma. This species is a species that's really difficult to see, as you can see on this image. And it's here on this image too. You have on the middle of this starting to get orange Hematococcus, you have a little bit of a Paraphysoderma here. They start small, you can see them, you just can see them on DIC microscopy, and they are really toxic for the algae. They have this inserting part of the body that goes inside the cell and takes out all the organic matter on the algae, and they stay just empty shells of the Hematococcus.
Sorry, could you move the other windows, because
sorry, it was in this computer. I'm sorry. Okay, I changed the bind. I think I thought that. So another part of contaminants that it's really tough to say and it's really tough to understand and have an idea about is most of the virus that affect our cultures. And this is really not well studied. It's really not well described, most of the virus that can collapse a culture, because algae we have a tendency to think that all the algae has this virus resistance and they are not going to be affected. But sometimes just a virus that you can see and you can control it, it's the toughest part of controlling, can kill your algae, and you are not going to find any type of normal contaminant that you normally have, or a fungi or a bacteria that may cause this type of exploding on your cell. You can see my mouse. Or this here on this Adulaniella culture, that this was a cell just 1 second before I took the photo. And this is because it was infested with a virus. So that way I want to show a little bit of examples of the contaminants that you can have on your cultures. Please, if you want to say anything in the middle, please stop me, okay? So, but to get there and to know what type of contaminants we have, we should know what makes us to have the contamination. So I just made a small list of some things that I think are important to mention to take care of what I can think about before having the contamination, so I don't have this problem in the future. And it's all of this here that I'm listing, and I will say a bit from each one, what I think may cause and it's just what I think may cause these things and what I have learned on the time doing some cultures of microalgae. And if you want to add something and then if you want to say something in the middle, please. So starting with light, we have this thing that most biologists or marine biologists will know, is that the zooplankton organisms, they prefer to graze on the dark, on the night period. So if you have a small light period on your culture, or if you have a culture that has shadowing on the middle of the day or something like that, you are going to stimulate these grazers organisms to graze on your algae. So even if you have a natural light culture, that's normally when we have a pond, we have natural light, it's okay to have a period of night from, I don't know, 8 hours and the rest of time of day. It's normal to have some grazers, it's normal to have some other organisms there, and they are not going to collapse your culture. However, if you start from having 6 hours of light or 4 lights of light on your culture, or more light on your culture, because you can have light, but you are in a little bit of a shadow during the day, and this already is going to be something that's going to make your grazers grow much more than with a normal light period. This is something that should be even thinking about putting some artificial light together in the day to make it to stand more the day and or to make it hotter during the day, so the grazers don't grow so much. My internet connection is unstable. I think I don't have anything I can do about that. Okay, temperature. It's important for you to know what's the exact temperature that you need to have on your culture. We have some algae that are special organisms that can go on different temperatures from 5 degrees to 45 degrees, like Tetraselmis. But most of these species will have a range of most 10 degrees on the water of difference. And these 10 degrees, if you are on the low part of, on the up part of it, you may have a temperature that's better for the contaminant of the algae than it's for the algae. It's very important to have really precise temperatures on your water. Even if you need to have a controlling temperature on your system, believe me, it's cheaper to have this controlled than you having to do everything again. Because when you have a contamination that takes out our culture because of the temperature that you don't have right, you are going to take time to discover that's the temperature. You are going to take batches of cultures that you are going to have to throw away until you find that you have to adjust your temperature 5 degrees so you don't have that contaminant growing. And it's easier to control your temperature than simply taking out the contaminant of the culture, because you can do that. You can clean a culture on a small batch culture in a laboratory. When you go to a pond, when you go to a green wall, taking out the contaminants is literally impossible because you have too many areas to take care, you have too many liters to take care, and it's too much difficult to clean it after it's on so much volume. The same thing with the pH. Normally we control pH with CO2 intaking. So if you have the CO2 intaking, you are always taking your pH a little bit lower because the algae are always making the pH go higher. So with this control, you have a little bit less problems on your algae. However, even because you have the CO2 intake on your algae, you can have this CO2 too much on your algae and making your culture getting on lower pH conditions. If this happens, again, you can have some fungi specified for lower pH growing, or it doesn't need to be really low, it can be 6. If your optimum of your algae that goes around 7.5 to 8 is on 6, your algae is going to not grow so much, and you are going to have a fungi growing and a bacteria growing much more than you are expecting it to grow on your microalgae. The same thing of salinity. If you have this species, this example that I gave here, the Thalassosira, it's easy to think that a marine species grows in any type of salinity from 20 to 35. However, the same thing of temperature, the same thing of the pH, they have the optimum quantity of salinity that you can have for that species that's going to avoid you have some contamination on it. And there is some type of contaminations like the paraphysomonas that may be a type of contaminant that if you have a little tiny bit of salinity less, they can grow better on your culture than your algae is growing. And again, what I want to tell you is that every type of parameter that you can control better is completely necessary for you to avoid type of contaminations. Again, imagine here that you have an algae like Dunaniella. I don't know if you have ever cultured Dunaniella or you have studied Dunaniella, but Dunaniella is a type of algae that doesn't have a really real cell wall. The cell wall of this algae, it's an algae that that's like a polysaccharide, and it's really sensible. So even if you go up with a slide on top of the cell, it's already enough for you to may explode your cell if you don't have enough volume to make it a little bit movable. So let me show you the Dunaniella again. So this is our one type of Dunaniella. Here it's 10 micrometer scale. So can I do that? Yes, I can. As you can see, they have from round forms to pure forms to more fusiform forms, and they have two flagella. And this type of forms they have is simply because they have a really flexible wall. But having a flexible wall, it's good because it's resistant for salinity, it's resistant for temperature, it's resistant for light. But with friction, it's really sensible. So any type of friction more that you have, and this really can be your bubble on the culture, it may cause that you have a bigger mortality on your cells. If you have a bigger mortality on your cells, you have more organic matter on your cells, on your media. If you have more organic matter on your media, you have more organisms that can consume that organic matter growing on your culture. And so you have to take care of this in consideration. Like if you have a Cocolithoporidium culture, like a Emiliana Huxley or some Pleurocrisis, they are the same as the Dunaniella. They have sensible cell walls. It's really pretty. We can see it really nice. You have a calcium carbonate carapace that looks tough, but as they are scales, they can break easily with the bubbling. So if this is the type of algae that normally we don't even use bubbling because it breaks really fast. So let's continue. Operation. So yeah, this is a part that there are two topics that I want to talk about. They are together. This is the open area and the where it's put your system for culture, like your green wall, or mostly your green wall or your open pond, your green. Why? Because the green wall and the open pond are the two systems that get more contamination, different from tubular reactors that are a little bit more closed. They have too much space for things to happen there. So for water to get inside with rain, to water get inside with some seawater that can be on the sides, and you have organisms that can go around your station like flies. You can have some arthropatha eggs growing on there. You can have some, I already saw some toad eggs on some open ponds. So these are type of culture systems that you are going to have a lot of things happening inside. And you have to take in consideration if you have a seawater pond, it would be best to have it far away from the sea, or at least a little bit far away on a greenhouse, to avoid as much as possible that you have the environment around your area, around your pond, to affect your culture. It's really important for you to take care of it, because I have seen some people thinking that they are culturing some algae, and on the end they have another completely different algae, and they don't even know why. Yeah, this is a problem that I wanted to cite because it's in one of our works on the Green Collab Institute, that we have a project now that's just on contaminants. And this project, we did a thesis with one of our students, that's Melissa, she's in the middle here, that she was seeing the contaminant sometimes. Sometimes she didn't see the contaminant, she would inoculate her algae, and she would have a lot of dead cells. And she would have her culture collapsing in 1-2 days without even having the contaminant present. This is because this type of organisms, they can have cysts, and the cysts they last an eternity, really. They can be dried, they can be on the oven, they can be with lichidea for some time. They are really resistant eggs, they are really resistant cysts. And just to do inoculation that you are not seeing your contaminants and you pass it for a bigger batch, you are going to lose your algae because of something that you can't see, and it's almost impossible to control. This is something that we were talking about before, that we were talking about the different algae that can grow in your culture. That when I showed the photo of the Bacillophyta with other species of algae, with green algae, you have some species that you want to culture that may have, I don't know, a niche that's good for, or a skeletonema that's good for feeding fish. You have 3 days of replication time. Sometimes you have 3.5 days of duplication time. And when you have, or a Dunaniella that has this type of duplication time, when you have this growing, I don't know, I contaminated my culture with another green algae, Tetraselmis. This Tetraselmis on a culture of Dunaniella, they are going to grow faster, stronger, and they're going to dominate our culture in frame of 3 days. They are going to dominate, because a Tetraselmis growing 1.5 day at most, the duplication time. Compared with 3 to 4 days duplication time, this is deadly. This can happen on freshwater too, with a culture of hematococcus that can be contaminated with Chlamydomonas, or a culture of isochrysis that can be contaminated with Nanochloropsis. And we had this happening on our lab. And even in species that the 2 species grow faster, like Phaeodactylum and Nanochloropsis, we already had the contamination of a Nanochloropsis taking over a culture of Phaeodactylum. So yeah, this happens, and this is just the a slip of taking care. When you are working with a culture, then you clean your area and you work with another culture, or the thing that you have your flame here and you are work a little bit up, and if you will go a little bit too much up, you have a culture on your side that's bubbling, and then you have a contamination. So it's really a little bit of details on taking care of the cultures that may avoid this type of contamination. So this is a topic that's not really well studied and not really well disseminated. That's sometimes what you have on your culture that you don't think that's a contaminant is going to generate some type of secondary substance that may start to make your culture gets lower. And this is going to make, like, imagine that you have a bacteria that's producing a type of compound that may make your culture is low from 1 to 2 days of duplication time. This is not going to help just that bacteria. It's going to help every other organism that's there that can consume your algae, and they make your culture get down. So this article here is not about this type of contamination. It's just an article about type of cultures. And here they say that you can have co-cultures, you can have accent cultures, you can have unialgal and mixed cultures. I like this type of the co-culture because this type of secondary metabolism, it's not sometimes something that can be bad. As we were saying in the beginning, not everything that looks like a contaminant is going to be a contaminant too. And there is already some studies, more than 100, that say that culturing algae with bacteria can help on the growth of the algae because you can have vitamins and you can have other type of supplements getting on your algae that may help the growth of your algae. So to finish this part of what drives the contamination, I would like to say that's everything that you can control and everything that you may take in consideration, from washing your hands to passing alcohol on your bench to making sure that all your green wall bags are well closed on the most part of it, making sure that you don't have shadow on your ponds. This is all small details. Training your personnel, because the people that are around the pond, if they don't know what they are really doing, this is going to cause contamination. All of these are key factors for having a contamination-free environment. So yeah, I wanted you to take from all this part of it that I said until now is that. And if you see a contamination, you can always Google it. So now we go for the part of taxonomy and what you can do, not just taxonomy, but how to identify the contaminants and what type of methods we have for identifying the contaminants. This is a part that's really difficult for me to talk here because it's not something that I can say that all Europe is going to have the same organism, or Portugal is going to serve the same organism as Serbia. Or it's not going to be the same organism. It's not going to have the same look like. They're always different. Besides, sometimes we have the paraphysoderma that always looks the same and always going to affect the nematococcus. Most of the contaminants are really specified for the region, and they're going to be more present in a region than another, depending on the temperature, depending on the type, if there is humid, if there is not humid, if you have more sun, if you have less sun. All of these are conditions that you have to have in consideration when thinking about your contamination. That's why I was saying that's the first thing that you do when you are looking for your contaminant is, I saw something different on my culture. The species of my algae, contaminant, and look for papers on the same region area, or if you are the only expert on your area, look for places that has the same temperature and the same conditions that you have. So about the differences on taxonomy and molecular identification. The two of the methods, you need really specified people, you really need to work a lot to identify. However, the part of the taxonomy is something that it's just on your region, and you have to study for your region and look for the specific things on your region, and you have to have a specialist just on that region. However, on molecular identification, you can have a person that works in the United States comes here and he does the same work that he's going to do there, he is doing here, because most of the part of the work is the same. The other difference is the price. Like taxonomy is virtually free. You have a personnel that's not going to do just that, and it's the person that's going to identify everything for you, and it's going to teach you other people. It's going to do anything that a technician can do, and you're already paying that person. However, on molecular identification, it's something that's really expensive. You have to buy kits, you have to buy primers, you have to design primers, you have to do the primers the way you think it's best, and then you try, and then you have to do it again. So this is the part of the expensive method. So about taxonomy, you normally go with microscopy. You can use inverted microscope. That's good for seeing low density cultures normally, or environmental samples, or a normal microscope that you can have, and you can take photos and you can take the documentation of our algae daily.
basis. And you have to know what type of microalgae and species that you can have always. The most important part to know the contaminants is to know your algae. So before I take 10 minutes talking of each part of algae, do you want me to talk about that, or it's too redundant?
No,
Okay. So cyanobacteria, I think you know that cyanobacteria, they can have different forms from small dots to really big filamentous organisms. This is a Trospera that I take, that I took a photo of Trospera plantensis on GIC. And on most environments of fresh water, you can have this algae taking care of your culture completely. With a culture of chlorella, you can have Arthrospora growing as fast as chlorella, and sometimes you're going to lose your chlorella because of that. Most of the other algae that I'll talk about here, it's not so fast as cyanobacteria on growing, but take care that the cyanobacteria, you can have some toxigenic species. Like you can have Cylindrospermopsis, you can have Microcystis, that are two species that you can have to, you normally take a look at it when you are talking about water bodies for consumption of humans, because they can kill, but you can have them growing on your biomass. And if you have them growing on your biomass, you don't want to sell that biomass because they are going to kill people. So chrysophytes, they are beautiful, they are nice, they are really tough to grow. So you have to know them, you have to know how to look at them and see some different things on their culture. But I don't think it's going to be a problem of contamination on any type of culture. This is a Thysochrysis, a Praminosa that they're beautiful brown balls and they grow really well if you want to try to grow them. However, they too can get contaminated with other type of species like Nanochloropsis salina. You have the diatoms. This is a Skeletonema on DIC. This is another type of algae that it's important to talk about the morphology of and taxonomy of it, because it's one of the most diverse type of classes that you can have. You separate the diatoms on pinnates and centric diatoms, and from pinnate and centric diatoms, you can look on several thousands of different types of books and have different images every time that you are looking at it. You have triangular forms, you have circular forms. This is just centered because the skeleton is centered. You can have star forms. It's really another world that you have to study just to know the taxonomy about the Bacillophyta. It's a completely different world and should be just one person looking for it. Every time that you want, you may have to need to, with taxonomy, to send it to at least a photo for a specialist. Cryptophytes, they look a lot like contaminants. You look at them, you see, this is a contaminant. And most of the time they are not, but sometimes they can be a contaminant of our algae because these are, some of them, they can be mixotrophic or heterotrophic on some points. And if they are heterotrophic or if they are mixotrophic, they can consume our small algae. And yeah, they eat your algae, basically. So this is the most common forms that are from around here. So I thought it would be nice to show you some photos of it. Dinoflagellates, these are some type of algae that are going to be difficult for you to have in our culture. I hope you don't have it because they normally need some specified media to grow and some really specific characteristics to grow. This is a Gymnodinum catenatum that we grow in our lab. And nothing else grows on the media of it, and it doesn't grow on any other media, but you have it on the water, and you may have to identify this on some time if you go for taxonomy to identify our contaminants. Euglenas, they are really different type of algae. They change a lot. They can have all types of forms. They are really malleable and beautiful. And this too is something that you can find on your culture, but it's not something that's really common. As you, I don't know if you know him, but this is a paper that is from here, from Serbia. That for you? I was looking for a photo and I thought, I found something from here, and I wanted to show. Thank you for the image. It's really nice. So yeah, you have this here. So this would be nice to know. And of course, the chlorophyta, the most common that we grow, that we normally have for food. This is a Tetraselmis striata. That's not really for food yet, but I think it's going to be soon. And we go for the taxonomy of the other organisms. As I was showing you the photos of the grazers, these two are organisms that they can have different forms and different type of functions on how your environment. And what can I say? This is really difficult to identify from the species, most of today's species. It's easy to say if it's a tintinid or if it's a verticella. If it's a verticella, when you are looking at the microscope, you are going to see really a vortex of water on it. And it's really nice because it has this type of cilius that does like this, and the algae are always going like this. It's crazy, it's awesome. It's something, this is a type of it. Or you can have tintinids. Tintinids are a type of grazers that they look like tulips or a glass of wine, basically, that they have these bases that it's really long and attached to some substrate, and they have this type of pulp that's like this. And they mostly wait for the algae or for the other thing that they're going to eat to come around and get sucked in. It's really nice to see it. And you have all the amoeba and other grazers that have natatory capacities, and they're going to go swimming around and eating your algae a lot. Like I have said, the pirella, I think it's a really nice thing to see at the microscope. So this is part of the taxonomy. This is a video that I was taking on another sample that I had, that as you can see on this video, I have at least three different types of grazers. This I couldn't identify it. I think it's snail some type or some type of parasites that I couldn't identify. This was far from my specialty, but this came from feeding of mollusks. This was together with the food of feeding of mollusks. These are some resin balls that were in the middle there for another reason. So I just wanted to show you how it would look like on a sample with some contaminants. Just for you to know, this is on slow-mo, okay? They're really much more faster than this. Normally you see this just like some flies flying around on the sample. So I think I will stop and just continue. Don't know how much time I took already. So, and if you want to specialize on identification, you should look for some specific courses or universal courses that you can have for taxonomy, and with different types of institutes that have international degree of international, I don't know how to say, but they are really recognized internationally by doing that. So it's institutes there, they have specific protocols to how to identify, to how to train people. And you go there, you train with them, and then you can train other people in your institute too. So if you want to go to taxonomy, look for that. That's important for you to have to be sure to have this on your institute. So together coupled with taxonomy, you can have a little bit of faster ways, because when you talk about contaminants and taxonomy, you have to take your sample, you have to count your sample, you have to fix your sample, you have to count your contaminants, you have to identify your contaminants on the fixation that you have, that may be formaldehyde, that may be gall, and each type of fixation that you have on your culture is going to change your contaminant form. So when you change the contaminant form, you are going to lose a little bit of the capacity of the taxonomy. So I brought this. That's a method that is, I just know this brand. Maybe we have another brand now. That's the FlowCam. That what does it does? It's a flow cytometry equipment. So it has a syringe that pulls your sample from here. And here you have a optical equipment with photography that may measure your cells from the volume and the structure, and take the fluorescence of your cells in account to make a library. And you can count your cells in less than a minute. You can count one entire experiment of cells. So you put there like 5 milliliters of cultures, and they are going to photograph all your samples, and they are going to characterize on the volume, on the size, and the fluorescence emission and the citation that you have on your samples. But this has to be made mostly by you. So you do the photos, you go there, take these photos in consideration. This is something that I did for Gymnodinium catenatum. These are cells that are individually, these are cells that are on bubble, and these are cells that are on 4 cells chains. So I did this, then I went to the program, made libraries with each one of these, and then I told them, so now you count for me every cell that's single, then you count every cell that's double times 2, and then you count every cell that's in with 4, you count times 4. It took me a lot of time and effort to do this library. However, after I had this library done, I would do all my samples in one day. I would count what I would count by hand in 2 weeks of work. So it's worth your time, and it's worth the time spent to do the libraries, but it's a little bit tough. So the other way to identify the contaminants is by molecular identification. And this you start with any kit of DNA extraction that you can have. You have kits of DNA extraction that are specific for plants, DNA extraction that are for soil, DNA extraction that are for humans, DNA extractions for everything that you have. You can buy your kit and try the kit that's best for your company and for your institute. So, okay, now I have a DNA extraction that have at least one algae and at least one other type of organism that's consuming my algae. What do I do to identify it? NGS. You send to the NGS analysis because you can know what type of parameter that you have to use to do your PCR. You don't know you don't know anything about your sample in reality if you're just going to the molecular identification. So you need to do a amplified of everything that you have there, so you can try to find what type of organism you are looking for. After you know what type of organism you are looking for, you can then draw your primer, and you can know what you want to do, and then you can go to do your PCR and optimize your PCR with the primer that you think it's best for you, or if you have to design your primer for you. And then after you have a good PCR sequence, then you go to the blast to identify your sequence and do a phylogenetic tree to identify what type of contaminant you have. This looks like a lot of effort. It is a lot of effort. Melissa is here that can't let me lie that she took 1 year to just do it for one algae. I think even less. So it's a lot of work, and in my opinion, this is not totally safe free if you don't at least know what type of organism you're looking at. So I think you should at least know a little bit of taxonomy to go to your molecular part, so you have a little bit less of a range to look for. And when you have your sequence and you're going to blast your sequence, you are not going to see like a paraphysoderma and it's an euglena or something like that. So it's good to know what you're looking at before you do the molecular. Even if you are going to the molecular, please at least Google it to see what is on your sample. And how to isolate the contaminants. This is an inverted microscope, and I hope we can have some time to do that on a normal microscope here tomorrow. That you can get a small needle. Normally we use a capillary that's a little bit stretched, and you go there and do bisection, take one cell from your culture. This cell from your culture can be the cell of the contaminant or the cell of the microalgae, you can choose it. And I would do the two, one that you can do a single cell DNA extraction, and then you can have just one type of organism there. That would be faster for you to do the molecular. And you can have now a clean type of microalgae culture that you can get there. So this is just the beginning. Normally what I do, I go there, I have some, no. We go there, we get some cell, we put it in another drop of media, we look at it, see if it's clean. Like you can see here, I have a lot of organic matter on this culture. So what I will do now, it's pass to another drop of water. After this drop of water, I will pass to another drop of water until I look at it and I see that's clean of at least the organic material that was around. Then I go with this to a plate. It can be a 96 well plate or a 24 well plate that's going to stay there with media and try to replicate and see if I can have another culture with good conditions. This is another type of isolation method that we have, that's self-sorting by flow cytometry. This is the model that we have on our institute now. That's the Faxaria, that it's not really on our institute, but it's in the same university and we can use it. That what does is to separate from size and type of complexity. It shoots a ray of light. It can be our light, or it can be a laser, or it can be another type of color. And it's with the scatter of this light, it calculates the size of the cell and the complexity of the cells and do a graph about that. And with this graph, it's going to be a lot of dots, a cloud of dots. And with this type of data, you can separate if it's eukaryote, if it's prokaryote, and then you can go to the fluorescence. You can choose on this equipment, you can choose two types of fluorescence to couple it. And then you can see the cells, the size of the cells, the complexity of the cells, and the two types of fluorescence to divide your cloud of dots in populations. And you can choose one of this population so it can sort on a 96 well plate. On this sorting, it can be a single cell sorting, or it can be 10 cell sorting, or it can be 100 cell sorting on the same well. And this is a way that you can have to separate even your fungi or your bacteria from a sample. I have seen something about virus on it, but I don't see it as something that I would try because of the size of the virus. But normally we can't get live grazers from this, because with the pressure that the separation of the single cell normally kills the grazers. But other type of organisms as amoebas it kills too. Bacteria, fungi, and some type of algae you can separate and you can isolate it with this method. It's a little bit more expensive than doing it by micromanipulation, a lot more expensive. But you can have a lot of samples in one day. So on the time, at the time now, I think I can do 2 plates of 24 wells of isolation in a day, in 4 hours a day. In this equipment, we can do 4 plates of 96 wells in 4 hours. So it's too much more efficient to do on cell cytometry. on a flow cytometry than doing by hand. Just if you have organisms that are more sensible, like amoebas, like Dunaniella again, or some type of cells that you think it's going to work on the flow cytometry, then it's worth to go to do the micromanipulation. Normally, I use micromanipulation to do the first sorting on environmental samples, or using for this type of organisms like dinoflagellates too. I don't use cell cytometry. I use the micromanipulation. And this is the title of the student of ours, Melissa, that she did this contamination detection on industrial microalgae cultures for 2 types of microalgae. I can't enter in more detail on this. I just wanted to show a little bit of this, and as I talked, because it's on convenience with the companies that we don't tell about the species on the contaminants. Just wanted to show the title of it, and thank you for attention. And I hope that you have some questions for me.
So we cannot see the PhD that you just showed. Is it available or not?
It's not available yet, but we hope to publish soon. It's because it's with the companies, and the companies are a little bit skeptical to publish it yet, but soon it's gonna be. But if you want more information, Melissa, she's here, and you can talk with her about that. It's going to be nice. Okay.
Question. You talk about the difficulties to isolate by molecular biology in general. Did you find some, I saw, for example, 18S, 16S, and so on. Did you find some generic primer that you can use?
For what?
Yeah, you're right, for contaminant.
No, yeah,
For contaminant.
it's not easy to tell you that, because just thinking about if you use the ITS tool, you are going to have so many things that you can identify anything.
Yeah.
The ITS tool would be the most universal of them, but you couldn't identify anything with the ITS tool because it's too much from everything, and it's too mutable, and it's not something that's really useful. But it's something nice to complement when you have your sequence split. Like you can have the 18S for audio, for example. You can have the 18S, you can have the 2FA, you can have the ITS2, and then you have a really nice complement to say what species that you have. But now about fungi, now about the grazers, the bacteria. The bacteria is easy. It's 16S and goes. However, for knowing what are all the bacteria that you have there, that's going to be a problem, because then you have to get your culture, you have to plate it on a PCA plate, and now the bacteria that grows on that PCA plate, you isolate, and after you isolate, then you do the 16S. The problem of using universal primers is that you get everything. And you are going to get everything for bacteria, and you are going to get everything for fungi, you are going to get everything for grazers, and this makes the universal primer not really what you want, because it's too much of everything and not really something that it's manageable after. The information that it gives you is not really information, it's just some noise.
From personal experience, it depends from your country. Of course, if you expect something on a natural environment, of course, you cannot use a generic primer. But personally, I use a conservative primer for acetyl carboxylate. It's quite conservative region. And you can identify at least green microalgae and some bacteria and fungi. But for grazers, for example, I do not have any specific targets. So if you add some targets for grazers.
Yeah, what we are going to work now, I understand what you are saying.
Yeah.
However, I don't have a primer that is going to give you a universal target for all the grazers. This is, in my opinion, almost impossible. You would have to get to genus at least to have a primer that is good for you. I don't know what type of cultures that you have. It's like green walls.
Yeah, they usually work with green algae or say.
No, what type of system that you use?
Alcohol.
A pound?
Yeah.
Yeah. So if you look at a pound, you have a lot of type of. You can have some insect eggs. You can have sometimes more than one type of grazer. You have some amoebas. You have some copepods. Sometimes, not always, but you have a lot of different things. And I would go for primers that are specific for each type of genus at least, because if not, it will. At least on my experience, I have a lot of noise. And on our case here, what we were trying to do is try to isolate primers for just that type of contaminants that we know that are bad for us. So like instead of going to universal, going to the specific, most specific possible, so you don't mind all the rest. I think it's best to go like that.
Thank you.
Someone else, please don't leave me alone.
Maybe just a general question. So how worried are you about having other organisms than the particular algae or cyanobacteria that you want to culture?
Depends. Depends on first. Depends on what the company wants, because normally we work with companies. It's not us that we are producing the algae, but if you have something for feeding, it's not really worry what type of things that you have inside. If it doesn't kill your culture, it's okay. But if you want something for pharmaceutical purposes, or if you want something for human feed, the control that you have to have, it's a little bit more specific. So mostly what we want is a closed environment and not killing our algae. The rest, it's okay.
So what is the type of quality control that you do? Because I'm, obviously I'm a researcher, so I have no clue what the practicalities are. But what is your quality control at the end when you harvest a product?
Depends. The quality control has to be done by the company, because it's already the part of the final product. And normally what we do, we solve the problem for the company, and the company continues doing the work that they do. What they want to do is normal food conditions like E. coli, Staphylococcus, and other type of bacteria that are prejudicial for humans. And we have the supplement qualifications. It's like when you have seeds or when you are going to eat grains or something like that. We have legislation that says how much dirty things you can have on your cultures. And they say there that it's like parts of insects, or it's types of other organisms that you can have, like sometimes you have feathers, sometimes you have some type of hair inside of your in your grains, and it's the same thing with the algae. You have a quantity of contamination that's okay to have. It's normally around, I think, 1%, if I'm not mistaken, of this other type of things that you can have on your culture. This considers too the grazers and the amoebas and the bacteria and the fungi that you have in your culture.
Yeah.
Okay.
Thanks.
Yeah, probably, yeah.
Yeah. Question.
We work a lot of times with wastewaters. So we have a pond and wastewater, and then no matter what we inoculate, we get something totally different. And it is usually Stenedismus, which is very interesting, sometimes even 100%. So, but of course, here is the playing between bacteria and algae. But sometimes the cultures collapse for no particular reason. So do you have any, did you think about how to know when does this whatever is inside becomes a contaminant? Because
This is the most difficult question that you could do. Because because even think about just the contaminants. When you talk about wastewater, it depends on what type of wastewater. If it's a city wastewater, if it's a fabric wastewater, what type of wastewater that you have, that's going to say to you what most type of contaminants can be there. But
usually can digestate, because digestate is, kind of unused fertilizer that is then stabilized and you can be used further.
yeah,
Yeah,
and it has a lot of things.
it has a lot of
So
things.
I don't know how to answer you because it's too random to say like which type of organism is going to proliferate at any time. If you usually have Cynodesmus growing there, depending of the type of Cynodesmus, the growth phase of it can have some type of not lag phase, but it's most likely it's going to diminish the growth for some type of period, and probably this type of when you have less growth is when your contaminant is going to tackle your culture. It's going to collapse your culture. So maybe if you already know that Cynodesmus is the algae that best grow there, you can try to reinforce your culture when you see that the culture is not growing so well. You inoculate again. Like having a controlled pond by the side of the wastewater pond and mixing it a little bit. Sometimes you just, my culture is not growing so well as yesterday. Let's add some 50 liters here, just to make sure that you have your cells always on exponential growth. That probably, I don't know, I'm just.
Yeah, okay. Thank you.
Thank you, Gabriel.